Hey everyone, and welcome. Ready to dive into the elegant universe?
Absolutely. Always up for a mind-bending journey through the cosmos. Brian Greene is a fantastic guide.
Right, and he tackles some seriously big questions like we're talking quantum mechanics, general relativity, even that ever-elusive theory of everything.
Exactly. And one of the things that always fascinates me is, well, if physics aims to explain how the universe works, like at the most basic level, shouldn't there be one set of rules?
You'd think so, right? One universe, one rulebook.
Yeah.
But Green points out there's a problem with that.
Yeah, a big problem. Our two best theories, general relativity, which is all about the large-scale universe, stars and galaxies, that stuff.
Right, the big picture.
Exactly. Well, that clashes with quantum mechanics, which rules the world of the very, very small.
It's like they're speaking different languages. So, is the universe truly divided? Like some kind of cosmic dual citizenship?
That's what's so intriguing. Green asks, are we missing a deeper connection? A hidden piece that brings everything together?
I like that, a hidden piece. So where do we even begin to search for that?
Well, Green dives into some pretty mind-bending concepts like Einstein's theory of relativity, for starters.
Okay, yeah, relativity, always a fun one.
Right. One of the things about relativity that just, blows my mind is the idea that nothing, not even gravity, can travel faster than light.
Wait, hold on. How did gravity even relate to light? Isn't gravity what keeps our feet on the ground?
That's the thing. We used to think, thanks to Newton, that gravity was this, instant force across any distance. But Einstein comes along and says, nope, not so fast. If light speed is the ultimate limit, gravity's got to follow the rules too.
So you're saying our understanding of gravity, of all things, was wrong.
Not wrong, exactly. More like incomplete. Einstein's genius was realizing that maybe, just maybe, we had space and time all wrong.
Time itself isn't as straightforward as we thought. Now we're talking. Tell me more.
Okay, so picture this. Space and time aren't just these rigid backdrops, but active participants in the cosmos. They warp, they curve, they respond to matter and energy.
It's like the universe is doing a cosmic dance.
Right. Think of space like a trampoline, a massive object like a star. It's like a bowling ball on that trampoline. Creates a dip, a curvature, and that curvature, that's what we experience as gravity.
Okay, so gravity's like a cosmic game of marbles. I love that analogy. But what about the other end of the spectrum? We've gone from galaxies to bowling balls. What happens when we zoom in on the truly tiny, the building blocks of everything?
Get ready to go down the rabbit hole. We're talking about the realm where even atoms are like giant universes.
So smaller than the smallest thing we can even picture.
Exactly. Green takes us on a trip from the ancient Greeks, who thought atoms were these indivisible bits of matter, to our modern picture, quarks, electrons, and get this, antimatter.
Like on Star Trek. They're always going on about antimatter.
It's not just science fiction, it's real, and it's a crucial part of our understanding of, well, everything.
Okay, I'm hooked. But I have to ask, what does all this antimatter, these quarks and electrons, what do they have to do with the universe, like holding together?
That, my friend, is where string theory comes in. Get ready, because this one's a doozy.
String theory. Okay, lay it on me. What's the deal with these strings?
Imagine this. Everything, and I mean everything, is made up of these incredibly tiny, vibrating strands of energy. We're not talking about little billiard balls anymore. We're talking about, tiny, vibrating guitar strings.
Okay, I'm visualizing tiny guitar strings now. But how do those strings become, well, everything?
Think about how a guitar works. You pluck a string, it vibrates, right? And that creates a specific note.
Different vibrations, different notes. I'm starting to see where you're going with this.
You got it. String theory says each unique vibration of a string, that's what creates a different particle or force. One vibration pattern might be an electron, another might be a photon, the particle of light. So basically, the whole universe at its most fundamental level is like a cosmic symphony.
Okay, that is seriously mind-blowing. We're not just made of stardust, we're made of music. Is that the elegant part of the elegant universe?
It's definitely elegant. But there's even more to it. See, for the math of string theory to work, you need more than just the three dimensions we experience. Up, down, left, right, forward, back.
Wait, hold on. You're saying there might be more dimensions than we can even see. Okay, now you're really blowing my mind.
Imagine you're an ant on a garden hose. The ant can crawl forward, backward, around the hose, right? That hose is their whole world, essentially two dimensions.
Got it. Life on the hose. Pretty limited ant real estate.
Exactly. But we can see the bigger picture. We see that the hose also curves. It has that circular part the ant can't perceive. That's kind of what string theory suggests, extra dimensions. Curled up so tiny, they're hidden from us.
So even though we can't see them, Those extra dimensions, they're still impacting how the universe works.
Exactly. They're like the behind the scenes crew of the universe. And get this, they might be the key to unifying general relativity and quantum mechanics.
Okay, now we're talking. How does string theory bridge that gap?
Let's talk black holes. Those are regions where gravity is so intense nothing, not even light, can escape. Einstein's theory predicts this point of infinite density at the center, a singularity.
A singularity, like the universe's error message.
Exactly. Our laws of physics, they kind of freak out. But string theory, with its vibrating strings, it might have a solution. Instead of infinite density, picture a tangled ball of strings vibrating super fast at the center of a black hole.
So string theory steps in to save the day, potentially. Pretty impressive. But what about the granddaddy of cosmic mysteries, the Big Bang? How does string theory tackle that?
Think back to how relativity and quantum mechanics clash in extreme conditions. Well, the Big Bang, that's the ultimate extreme, going from smaller than an atom to the entire universe.
That's like the universe's biggest, most explosive magic trick.
And those extra dimensions we talked about, they might play a role here too. Some physicists believe that in the very, very beginning, those extra dimensions were curled up differently than they are now.
So not a Big Bang, but a big unfurling. Now that's a visual.
Right. It highlights how string theory isn't just about, adding dimensions for fun. These extra dimensions, they might explain the origin of the universe itself.
Okay, I have to ask, this all sounds incredible, but is there any way to prove it? How do we test string theory, especially these extra dimensions?
That is the million-dollar question. And as Greene makes it clear, string theory, while elegant and potentially revolutionary, it's still a work in progress. We haven't figured out how to test its predictions, not definitively.
So we've got the treasure map, but not the X that marks the spot. We know where we want to go, but actually getting there is a whole other quest.
A good analogy, but even without direct proof, string theory has changed how physicists think. It's like it's opened up entirely new ways of looking at the universe.
Like a new set of lenses to see the cosmos, even if they're not perfectly focused yet.
Precisely. It's encouraged us to think beyond our usual three-dimensional box.
And speaking of thinking outside the box, Greene doesn't stop at extra dimensions. He takes us even further down the rabbit hole into the mind-blowing concept of the multiverse. The multiverse, okay, that's a big one. Multiple universes existing all at the same time. Even for a deep dive, that's a lot to wrap my head around. That's like serious science fiction stuff. You're saying string theory actually supports that idea.
It does. The equations behind string theory and its even more mysterious cousin, M theory, they seem to allow for not just one, but a whole bunch of solutions, like a huge number. And each of those solutions, that could be a whole different universe with its own laws of physics, its own, fundamental settings, even its own kinds of matter and energy.
So not just one universe with one rule book, but like a cosmic library of universes. Or we're talking about universes where gravity works in reverse, where time runs backward.
That's the exciting part. It really opens up the possibilities. We don't really know the full range of what could be out there in this theoretical multiverse. Some might be similar to ours, just with small differences. Others, though, they could be so wildly different with forces and particles we can't even imagine. We might not even recognize them as universes.
That's kind of amazing, but also a little strange to think about, right? Like, if there are infinite possibilities, does that mean our universe, the one with, stars and planets and life, is that just a random fluke?
That's a huge philosophical question that comes up with the multiverse idea. Does our existence mean anything in the grand scheme of things if there are infinite possibilities? It's a debate going on right now in the scientific community. Some people think that with an infinite multiverse, universes like ours, with the right conditions for life, they're bound to happen eventually just by chance. Others think maybe there's something else going on, some kind of guiding principle that makes universes more likely to form in a way that could support life.
So it's like, with enough rolls of the dice, you're bound to get lucky eventually. Is that what makes our existence special? Or is it just a cosmic coincidence? But how could we ever know? If we can't see past the edges of our own universe, how could we ever prove or disprove the multiverse?
That's the challenge. Seeing another universe directly, that might be impossible, at least with what we know now about physics and our technology. But it doesn't mean we're totally in the dark. Physicists are looking for clues, for any hints of the multiverse that might have left a mark on our own universe. Like, imagine trying to find patterns in the cosmic microwave background radiation, that faint echo of the Big Bang. Maybe, just maybe, there are signs there of interactions with other universes way back in the beginning.
It's like trying to read a message in a bottle that's washed up on shore from a cosmic ocean. So much of this pushes the limits of what we can observe and really even understand, even if we never definitively prove the multiverse. I mean, what does just the idea of it, the possibility tell us about, well, about us and our place in all of this?
I think it reminds us just how vast and mysterious the cosmos really is. It challenges us to rethink our assumptions about what's normal and what's possible. It makes us reconsider reality itself. Are we really just one tiny bubble in an unimaginably vast multiverse? Are there other versions of us out there living out different lives in these parallel universes? Those are questions that go way beyond physics. They make us think about philosophy, about the meaning of existence itself.
It's definitely humbling and more than a little awe-inspiring to think about those kinds of questions. As we wrap up our deep dive here, what are your biggest takeaways from exploring these mind-bending ideas with Brian Greene?
It really drives home the point that we're still in the very early stages of figuring out the universe's greatest secrets. String theory, M theory, the multiverse. These are all cutting-edge ideas pushing the boundaries of what we know. We might not have all the answers yet, but it's pushing us to ask bigger and bolder questions, to imagine things that we once thought were just, science fiction.
It's an incredible time to be thinking about these things, and Greene does an amazing job not just explaining these really complex ideas, but also conveying that sense of wonder that drives scientific exploration in the first place. He really emphasizes that even when we're dealing with the biggest, most challenging questions, there's still a sense of beauty and elegance to the universe, and to our quest to understand it.
Absolutely. He shows us how physics, even though it might seem really complicated on the surface, deep down, it's all about wanting to understand the universe, to understand our place in it all.
Well said. And on that note, we've come to the end of our deep dive into Brian Greene's The Elegant Universe. We've journeyed from the tiniest vibrating strings to the mind-blowing expanse of the multiverse. We've encountered black holes, extra dimensions, and questions that really make us rethink the nature of reality itself.
It's been quite a journey.
It really has. And for our listeners, this is just the beginning. If you really want to dig deeper into these incredible ideas, I can't recommend The Elegant Universe enough. It's a fantastic read. Until next time, stay curious, keep those imaginations open, and never stop exploring the wonders of the universe.